welcome to this lecture on active noise control in the course on noise control in mechanical systems. So, this is our continuation of the previous lecture where we have begun the strategy for active noise control, where active noise control was introduced, what is it and what is the basic architecture of an ANC system and the basic components inside an ANC system and some of the common types of an ANC system, such as what do you mean by a feed forward ANC, then a feedback ANC, okay. And similarly there are things such as adaptive ANC, hybrid ANC, okay. So, these kind of things. So, in today's outline what we will do is that in this lecture we will review a few of the ANC techniques that have been applied in the field of machinery noise control, because this course is based around noise control in mechanical systems. So, let us see some case studies from the published papers. So, before that we will review two papers where they have used an adaptive ANC system. So, what is an adaptive ANC system? It is very simple, similar to the hybrid ANC system which was introduced in the previous class. And what happens there is that there were two microphones. So, one microphone was facing in the ambient environment near the source, which then gave the feedback. So, from the ambient, from the first microphone a reference signal was generated and given to the DSP, which then provided for. So, this is a typical architecture of an adaptive ANC system that has two sensors. So, what happens here is that let us say we have some noise source and it is emitting some sound waves. So, near the noise source slightly away from the listener there is a microphone that faces the noise source, and this microphone or the feed forward microphone, in the previous lecture I had called it the feed forward microphone, or you can call it as the reference microphone. It first measures the sound signals generated by the source, okay. So, it is located near the source and then it creates a reference signal. Okay. So, this reference signal then means that it is sort of a representation of the noise measured near the source. Okay. This is what the reference signal is. It corresponds to the sound signal, the sound waves generated by the source as measured by the source as measured by the reference microphone. So, that becomes your reference signal, which then reaches the DSP or the digital signal processor. The digital signal processor, through its various kind of electrical circuits and electronics, it is able to create an anti-noise signal. So, finally, this generates an anti-noise signal based on the reference signal that has been created. So, for a very simplistic setup, suppose we had some reference signal xt, let us say, then it will create something which is antiphase of xt, or simply whatever is x t, it would be antiphase of it or simply negative. Given that if x t can be represented as a sine wave, it will give you an antiphase signal, let us say capital X t, which is 180 degree out of phase of the reference signal x t, and then this signal would be sent to the secondary loudspeaker or the anti-noise source, which will then create this reference signal out of phase, and hopefully these should cancel each other near the listener's ear and there should be noise reduction at the listener ear. But that not always happens. So, why do we need the error microphone? First of all, whatever is the measurement here, we can never be sure that the signal measured here is the same as what signal actually reaches the receiver's ear. Yeah, because the signal goes through so many distortions along the path. It may undergo, first of all, if it is a spherical sound source, anyways as it goes away, if it is a spherical or a cylindrical sound source, with the distance and the propagation, the amplitude anyways attenuates, the amplitude decreases, At the same time, due to the various structural objects present in the pathway, there could be diffractions and scatterings. So, due to these various path effects, diffraction and scattering effects, the signal actually reaching the listener's ear could be slightly distorted compared to what was actually measured by the reference microphone. So, the reference signal may not exactly, so the signal reaching the receiver, let us say this is YT, this is the signal actually reaching the receiver. This YT could be some kind of XT, the reference signal, plus some kind of additional factors, let us say some factors F, which account for the various diffractions, distortions, attenuations, whatever it underwent while reaching the receiver's ear. Okay. So, some factors which could be function of various things. Okay. So, this is not exactly XT, but XT with slightly distorted elements. So, that is why for to make a more adaptive and accurate system, a second microphone is installed very close to the listener, that is called as the error microphone. What it does is, it measures what is the sound actually reaching the receiver. So, it will not measure the sound actually reaching the receiver. What it will measure, because by the time what happens, the reference microphone is measuring the sound, sending the reference signal to the DSP, and the DSP is generating the anti-noise signal which is being emitted here through this loudspeaker. Near the listener's ear the cancellations have happened. So, near the listener ear, what is it? It is XT plus capital XT. Okay, the two have. Now, if suppose there was perfect out of phase, if suppose there was no distortion, whatever signal was measured at the reference microphone, exactly that same signal reached the listener's ear, then XT plus capital XT, given it's everything can be represented as a sinusoidal wave, would ultimately cancel each other out, because it is just the opposite of the previous signal and we should get 0. So, ideally error microphone should measure 0, but situations are never ideal. So, it is never 0 actually, but in practice it is never 0. The signal measured at the error microphone, let us call it YT. Okay, YT is the signal reaching the receiver. So, let us call the signal at the error microphone as small et. This is small et, which is what? It is XT plus capital XT. So, in practice this signal measured at the error microphone is never equal to 0, but what is the purpose is that for a good ANC system it should try to minimize, okay, minimize the error signal. So, this becomes sort of like the objective, that you should make the error signal as less as possible, so that as near perfect cancellation can be achieved. Okay. So, it measures this, and because of the various distortions that might happen or some other kind of noise over here, it is never 0. So, this error microphone will sense what is the error between achieving a perfect cancellation and actually having something. So, whatever is the error it is measuring, so this should be minimized to 0. So, this error microphone will then send up a new signal, which is the error signal. Okay. So, this first microphone send the reference signal, this is going to send you the error signal. Okay. This will also go to the DSP, and now the digital signal processor has got the reference signal and the error signal, and if it is a very fast processing circuit, then the time lag between the reference signal and the error signal should not be very much. If it is too huge, then obviously it does not work for the high frequency components. Like in the previous lecture we saw that for if it is a feedback or this kind of a system, then for high frequencies where the fluctuations are very fast or in a highly rapid environment, then the time lag, the short time lag between the reference signal and error signal will make impact. But in a more steadier environment, this very fraction of time lag between the reference signal and the error signal does not matter. And then when the DSP has all this information, what it does is, once it receives the error signal, it does what? It takes the original reference signal and does some filtering to it in order to reach a new adjusted reference signal, and then from the second time onwards, a new adjusted anti-noise signal is sent to the speaker for creating, and then the speaker creates the after adjusting the reference signal, it creates a new adjusted reference signal, which is then emitted near the listener's ear, and once again the error microphone will catch what is the new error signal, and hopefully the error signal at the first time instance. Okay, this is like the assumption that the error signal at some time instance t should be greater than the error signal at the very next time cycle, and so on. So, slowly and slowly with each pass the error signal gets minimized and the system adapts to give as perfect cancellation as possible. So, these are the terminologies I already discussed through the diagram: what is reference microphone, error microphone, the reference signal, and the secondary source or the secondary loudspeaker, also called as the anti-noise speaker. Now, I already told you that once we receive reference signal, and in the first pass we just create an anti-noise signal, and then in the second pass, once the error signal is received, we readjust our anti-noise signal and emit the new adjusted anti-noise signal or the new sort of adapted anti-noise signal. So, we are doing some filtering to the already existing anti-noise signal. So, why is the need to do this kind of filtering? Why is the need to do this kind of adjusting? First of all, already explained to you that there could be, so the first reason could be that the noise signal that was measured at the reference microphone may not be exactly the same noise signal that actually reached the receiver, and because the anti-noise signal that was initially created is directly based on the reference signal, so hence perfect cancellation may not be achieved, because whatever was measured initially, it will go through some distortions to reach finally the receiver's ear, and hence the adjustment needs to be made to the anti-noise signal to get that cancellation effect, perfect cancellation. The second is that once the anti-noise signal is generated, if you can see here, so there is first the signal from here till here will have certain distortions. So, yt would not be exactly same as xt. In the same way, whatever anti-noise signal is sent from the DSP. Okay, so let us say this anti-noise signal is capital XT. So, this is the capital XT from the DSP. Okay, and then there is some capital, and this is the actual capital XT which is emitted at the speaker. Okay. So, because these are all internal electrical components, they have their own resistance and their own transfer functions and frequency responses. So, obviously based on, suppose if you are using very long cables or poor quality cables, poor quality speakers or amplifiers, what exactly the processor is generating, this anti-noise signal XT at DSP, there could be some distortions while this wave or this signal is passing through the various cables, amplifiers and to the speakers, and hence the actual signal that is being emitted outside may still be distorted. So, XT at the speaker could again be the XT that was actually created at the DSP plus some distortions. Okay. So, some additional distortions that have distorted it. So, these are the various distortions, and hence the need for an error microphone and adapting based on every pass. Okay, so these are the different, so that is why the anti-noise signal, some filters are required so that it can adapt in real time to the changes that the sound waves are undergoing. So, one of the very common filtering technique that is used in these various ANC system is the Filtered-X least mean square algorithm. So, what we want to do is that suppose we want our error signal, our anti-noise signal, expected anti-noise signal should completely, or the two signals should be exactly out of phase for perfect cancellation, but suppose our set standard is that there should be a flat response, but actually the error signal that we are getting, let us say this is our actual error signal that we measure at the reference microphone, and this is the 0 level. Okay, we want it to be at 0 level, but it is not. So, this is our expected graph, but we are getting some error as ET. So, this is the true value of ET, and this is the actual E dash T. If you call it as the actual measured error signal, then you want to minimize the difference between the expected error signal, which should be 0, and the actual measured error signal, which is not 0 but some value. So, to minimize the difference between the two graphs, we are trying to do like a curve fitting, the typical least mean square which we use, so that the because it is a digital signal processing. So, the the sum of the least mean squares means that the sum of the squares, you have to minimize the the sum of the square of these distances, okay, these distances, which means, so a typical LMS algorithm means that we minimize whole square, because sometimes it will be positive and negative. So, we are trying to minimize the square of the distance between the two graphs. So, this means the least mean square algorithm, but then to top that we have the Filtered-X. Again, in this course I am not giving you the detailed algorithm because that would be out of scope for the current course, but just a brief overview of just like we use how we minimize the root mean square errors. Here we are minimizing the mean square errors between the two expected error signal and the actual measured error signal, and with each pass our whatever we try to minimize this error or the square of the difference between the two signal. And then Filtered-X is an additional advancement to the LMS algorithm, where what happens, some adaptive filters or weights are added. So these weights could be dependent on the frequencies and the time. So, this is also added to so in top of the fact that we have to minimize this, we also add certain weights to the sort of received the weights to sort of this error signal, sorry, the weights to the anti-noise signal, so that we can minimize the error. Okay. So, with this let us see two papers. One is the active noise control in agricultural machines, published in 2002, and this is the reference of the paper here. So, what they have done in this paper is that they are adapting some ANC strategies to reduce low frequency cabin noise in agricultural machines, and then they have taken the case study of a harvester machine, which I can show you here. This is the harvester machine where ANC was applied. It generates a lot of noise, and obviously the objective is that whatever is the operator who is working on these machines, near the operator we should be able to reduce the noise, which is mostly low frequency. So, because the PNC methods, they are ineffective, or they are only effective in the high frequency zone, they were not they were found to be inefficient to reduce the harvester machine noise. So, ANC strategy was adopted. The authors have seen how 3 different types of ANC strategies are working for this particular case study. So, first they have used the feed forward control, then the feed forward with feedback compensation, and then the feedback control. So, here the feed forward control and the feedback control, they are the same as what I have discussed in the previous lecture, where you just use one microphone in feed forward, which is the reference microphone, and generate your signal. In the feedback, you only use the error microphone. So, you use, instead of having a microphone near the source, you have a microphone near the listener's ear, okay, and only that signal you use, and once you combine both of them together, you get this second kind of technique, where both the reference and where 2 microphones essentially would be used, both near the source and as well as near the receiver, in order to adapt. So, all 3 versions were applied. Okay. So, here for the feed forward ANC technique, a 1x2x2 system was used for doing the experiment. So, it was tested using 1 reference signal, 2 secondary sources, and 2 error microphones. 2 loudspeakers were used, situated on the left and the right behind the driver's seat, and they were used to reduce the noise level at the 2-error microphones close to the ears. So, the advancement they have done is that instead of having a single error microphone, they are using 2-error microphones in order to minimize and make the system more accurate as much as possible. Okay, and the Filtered-X LMS algorithm was used for this adapt in order to create the anti-noise signals and make it adapt in real time to the changing sound signals. Okay. So, what was happening is that here the quality of the reference signal determines a lot what is the success of the feed forward control, and hence good coherence and consequently good reference signals can be found only on certain parts of the machine. Because of the main challenge was we want to obtain, because the quality, because it is a complex machinery, the harvester machine. So, at different points of the harvester machine different kind of sound signals could be present, as in the sounds, the SPL distribution across the machinery may be quite uneven, and the source could be very directive in nature, and hence where should we measure the reference signal? That is what the authors faced as a challenge, that we want to create a good quality, a more representative reference signal. Okay. So, for that, how to find out what is the location where we should measure these reference signals, they had done the sound intensity scans, or simply we call it as noise mapping, to find out what are what is the distribution around the harvester machine and what are the zones of high sound intensities, and based on that they selected the zones or the places where they would measure the reference signal. Okay, this shows the intensity scans of the various compartments within the machines. Okay, this shows the measurement of the coherence near the front tools and the coherence at the different places in this particular figure. So, this is near the motor and this is near the front tools. So, good coherence was found near the front tools, okay, at various kind of frequencies, which indicates that these front tools are responsible for the main part of the noise inside the cabin. So, once the main noise source was identified, then the reference signal was collected and this algorithm was implemented. So, the reference signal was collected where they found the best coherence, and they selected that as they chose that as the location for collecting the reference signal. Okay. So, this shows the result of adapting the feed forward ANC technique. So, here the solid line, if you can see, is when it is the SPL dB versus frequency distribution when no ANC was working. So, you had a high dB versus frequency, but when ANC was adopted, this lighter lines, okay, this one indicates without the ANC. So, as you can see, the sort of performance of this ANC was very frequency dependent. So, at the low frequencies, you do not see at many of these frequencies much difference between the two algorithms, but in certain frequencies like these, there is a high difference. So, high level of the ANC is found to be very effective in certain frequencies. So, this shows typical frequencies and the reduction achieved in decibels. Okay. This is another representation of the same result. You can see that here you have more effective, okay, in these two areas, whereas in the rest of them the feed forward was not as effective. So, then feed forward control with feedback compensation was implemented. So, what is it in the previous technique, because the results were not up to the mark, because only in some frequencies, a couple of the frequencies, some good amount of decibel reduction was found, and then for the rest of them effectively there was no reduction in levels. So, the new technique was implemented. So, here using a microphone as reference sensor in the same acoustic enclosure where the secondary sources are placed became a problematic because of feedback effect. Anyways, this shows the feed forward ANC system with feedback neutralization, because what they found was that wherever they were measuring the reference signal, they had an acoustic enclosure, and then that was distorting their result, and that is why some compensation had to be made in order to make the results better. And again, I will not go into the details of this method, but rather just focus on what algorithm worked for them. So, what they found was that once they adopted some additional compensation for the acoustic feedback that is being received from the acoustic enclosures where the in the cabin where the speakers were being played. So, once that compensation was done, there was remarkable improvement overall in the reduction. Then feedback ANC was used with single channel, single input, single output systems like this, and then multi-channel systems were also used in this. So with increasing the number of channels for receiving the signals as well as processing and sending the anti-noise signal. So see, the single input, single output simply means that sort of the entire ANC or the entire thing is being done just on across one channel. So you have one reference signal, one error signal like that, and you are doing the adaptation. But in the multiple input, multiple output systems, what you have is you have multiple channels doing the same things. So from various other various locations, you are getting various kind of reference signals, various kind of error signals. You are doing all of that, and you are getting. So when you increase the number of channels for processing the ANC algorithm, so you receive more data from the reference microphone. So you have you have multiple reference microphones, you have multiple error microphones, and then the DSP processes the signals of the corresponding reference and error microphone pair in the multiple channels, and it generates the ANC, the anti-noise signal. Then in that case the performance is much better. That is what they had found. So finally the second paper, here the applications of adaptive feedback active noise control system is being done. Okay, this is the reference of the paper. Here a single channel broadband feed forward ANC system was used, okay, and with the same Filtered-X LMS algorithm. If you are interested to know how this algorithm works, you can obviously do a separate reading and see, but we can't discuss it within this course. So just we are giving a brief overview of it. And then so this single channel adaptive feedback active noise control system was used, and where it was used to reduce the industrial machine noise in some of the large manufacturing plants. So that was the goal for it. This shows the various circuitry, which again we will not be discussing within this course. Okay. So an experiment was done where you had the engine within a welding power generator machine. Okay. So this was taken as the case study, and a muffler was implemented, and then there was the ANC system. This shows the error signal and the ANC system that was implemented. This shows, so basically in a welding generator machine which creates high amount of noise, the ANC was implemented, and a comparison shows this is when ANC is off and this is when ANC is on, and you can see marked improvement in some of the low frequency ranges smaller than 200 Hz. So here you had a good performance, and then in the high frequency ranges the performance is not, it's almost making no difference at all, but all the high peaks got attenuated at these various kind of harmonics or peak. So whatever were the peak harmonics, they got attenuated by the ANC system. So with this I would like to close this lecture, which briefly discuss the case studies of where ANC has been applied in machinery noise control. Thank you.